Hi and welcome. Today we're going to play sound on PlayStation Portable, and we're going to do it very low level. You could use a audio library, I guess, but I didn't get that to work, so we're going to do it low level, and we're even going to load the WAV file really low level. We did that with texture files before, just converting them to a C file, and that's exactly what we're going to do here. So we're going to get into the WAV file format a bit to be able to do this, to read the file. But that's just the fun of it, and if you like to use the dependency to load it, then please use the dependency to load it. This is how to load it without the dependency. I already coded this code this time, so it's not a live coding exercise. I had a little health issues. I had an operation, and I actually coded this before the operation. So I'm just going to walk through it. Can start it first though. So it's just a drum that's playing on the PlayStation Portable, and that's all we need to verify that we have sound playing. So we have our sound here. Go to our WAV file, and we can see what type it is. If you have Unix commands, you can use file for getting a little bit more information about the file. In this case, it says it's a riff file. It's little endian. It's data, a little endian data. It's WAV audio. It's Microsoft PCM audio format. It's 16-bit and 44K. So that's some information about it. Let's go matrix on this shit and look at it. Here we go. Here we got the file. It starts. Let's wait. Let's draw something here. Where is my pointer? Up here is my pointer. Start with riff. It's 4 byte. You normally have 4 bytes that identifies a file. Not always, but many files has that. It's not like the computer needs, it's just more convention, like it's a good thing to do. It's called a magic header. It's normally 4 bytes. And the magic header for an audio file in this format is called riff. Then after that, we have something we can't read. And then it says wave. And after that it says FMT space, which in this context means format. Then we have things we cannot read. I can't even see where I'm drawing. And then we have data. And then we have more stuff that we cannot read. And it continues with just more stuff we cannot read for the full page here. So after riff, we have DAI00. We can figure out what those numbers are, and I can say that I happen to know that that's almost the file size. It's a chunk size, but whatever, we can call it file size. Then we got wave, then we got FMT, and we got more or less the same thing here. Got the size, and after here we also got the size. We need to figure out those sizes before we can read this. So let's jump out, or let's get my pointer back. There we go. And we have a command called object dump. And we're going to dump it in type, hexadecimal 1 byte each, and I want ASCII also. Oh yeah, for those that haven't used Unix much, you can pipe things to another program, and less is more. So if you haven't used DOS, you know the more command, less is the same. So here we go. We got start with riff, start with something, and then null null. And then we can see what I'm guessing is the size of the file. I happen to know it's the chunk size up there. So we need just to go to decimal, hexadecimal to decimal converter. And we just type in this, and I already typed in this because I needed to re-record this video because I recorded without audio. Brilliant for 30 minutes. But it's I wrote it enter hex number 00069DA, but here it says DA6900. And that is since we were talking about little endian. So you have different way you can store numbers in the CPU. Either you can just store them like in what order you expect. So you could say like, hey, I start to store here and then I store that direction, all my 4 bytes for an integer is 4 bytes. Or I could just be an idiot and say like, no, I want to store here first, then there, and then we're going to store here, and why not the last byte there, just to mess it up. So if human tries to read it, it's just like, I don't know what that is. So that's exactly what's going on here. So we got 0, that's our least significant byte. Then we got our next least significant byte, and then we got our least highest significant and highest significant, whatever, whichever order this is. But that's why I needed to convert this 0069DA here in that way. So it says DA6900 here, but 0069DA. And to be honest, I don't know the order. I just know that the little endian screws things up, and when I see a number like this, I'm like moving them around, like, yeah, that seems fine. And then we get a number here, 27098, but the file size happened to be 27106, so it differs by 8 bytes. But 8 bytes happens to be these 4, that's the magic of the file, and the size that actually stores the size. So that's 8 byte. So that just tells us how much comes after. So let's go into the code and see that we actually use that in the code. And here we go. RIF wave file format consists of chunk data. Chunk RIF. Chunk ID start with RIF. Chunk size is a little endian. Has 8 plus chunk size is equal to file size. And as it says, after that comes format. It says wave. And we had that in the data. Let's pick up the data again. Not that one. Let's pick up the matrix shit. There we go. And if you haven't seen the Matrix movie, please see it. It's a wonderful movie. So there we have the header of it. And that part apparently describes the size of all of this. Then we got FMT and something, and let's take a guess that that's also the size of the data until here. We get up to the next chunk that's called data, and I guess that's the size of the rest of the stuff here. So we got the chunk that says FMT. We had the FMT. We guessed that it was a chunk size, and that's correct. And let's come what format it is in. And this audio format, we happen to see that with PCM and 16-bit. Number of channels was 1, so it's mono. Sample rate for 0.1. A byte rate and a block a line, which I do not know why they include, because you can calculate those from the other numbers here, so it's more like a checksum. And bits per sample. And to verify what we expected here, we use the file format again. And we see that let's do it again so I can see it, since I have the camera in the way. So there's a wave audio, we know that's the wave. PCM, apparently a 16-bit mono 441K. And I have code that actually verifies that that's a file in that format we are using, and that's the code down here. So we just take memory pointer, and then with some pointer magic, we just assign these variables, and then I verify these variables after. So it's a RIF, it's a wave, it has a format, size 16 bits is a PCM, the size of it, and all of that. And let's go to the initialization of the PlayStation. So what we're first going to do is we're going to create a sample, and this sample here is a struct, and that struct has some data. I don't really need this struct, to be honest, but I have it, so I use it. It contains a format, frequency, size, loop, weight, and data. Those two are the two important parts. Weight and data. So it creates from the sound, it creates up the struct. It sets up the exit callbacks on the PlayStation. We can press the home button and quit out from the PlayStation. It calls the audios initialize. It calls audio init, PSP audio init, PSP audio set channel callback. That's the callback that fills in the hardware buffer. And then we PSP audio set volume, then we're creating something called a semaphore. Let's see if I have some space to draw on. And we have, okay. Yeah, that's fine, that's fine. Just draw over on my code here. So we got the VAV. This is in hardware memory, in our program's memory. And then we have the hardware buffer. That's when we are playing. We're playing from the buffer, and when it comes to the end, it goes around and it starts from the beginning again. And I can see that the blue isn't really possible to see with the background here. So yes, let's fix that. Much better. So we got a hardware buffer that is playing, that is looping around when it has been playing enough. So we need to constantly fill up this buffer from our sample. So we got the hardware thread that runs on the CPU. It runs there, and it calls in to a function that I define for the callback to make this to fill in the VAB to the hardware. And then we got the CPU, the thread that my program is running on, and that also needs to modify data. It needs to modify this wave data up here in the memory, because it has add a new sample. Maybe someone did something in the game. We need to play another sound, so we need to access to that memory. And both of these cannot do this access at the same time, because then we can get corruption. You would hear it directly. So we need something called a semaphore. And we got, that's like a flag that has a number assigned to it. So it has a number assigned to it, 1. So the hardware says here, hey, I want to do things, but first I need this flag. I want to grab this flag. I'm going to grab it I'm going to decrement this value. And I can see if I decremented it down to 0 or not. And if I did, then I know it's fine, I can run. And if the CPU needs to do something, it tries to do the same thing, but it doesn't manage to decrement it because it's already at 0. So it's like, I want to decrement to see if I was the one that decremented the 0. No, I was not. Crap, I'm not allowed to do anything, and then it retries. So this is called a semaphore or a mutex. Feel that explanation was a bit messy, but it's a second try to record it, and I'm hungry, so let's go with it. So let's see where we was. We were in the setup. We had made a setup. So the setup called PSP init audio. It called channel callback, and it created this mutex that's needed. And then it checks if it's running, and it says sample play, and it sleeps. And if we press home and press exit, we do audio initialize, and the initialize do PSP audio end pre and PSP audio end. They could probably have one method for that, but they do not. And then we delete this semaphore. Let's check in play. So the play here, wait for the semaphore to be open. Kernel wait semaphore. So trying to grab that semaphore, and what is really is doing is having a memory address that we know that are not cached. So we can try to decrement it, and if we were able to decrement it and got it to 0, then we know, oh, I got this semaphore. No one else can decrement it to 0 because it's already at 0. I can run this code. Then I run this code, and then I release the semaphore and say, hey, I'm done with the semaphore. You can set it back to 1 now, please. And it goes out. And then we have the other code that's called from us unknowingly when the play, we know when that play is called because that's us calling it. But this audio callback is called from the hardware to fill in the hardware buffer. And it sends in the hardware buffer here. And that one is also needed to try to grab this semaphore to know it's just me messing around with memory here. And then we're going to play the samples, or more correctly, we're going to fill in the samples in the hardware buffer. So we can have a number of samples playing because we are software mixing it now. We have a number of hardware channels in the, let's see if it's done in the, do it send in the channel here? It does not. Anyhow, I think it has a number of hardware channels. At least this has one. So the audio buffer here is the hardware buffer. So we're doing software mixing first, mixing in multiple samples. So say like if you have a background music in the game, you have a player shooting something and you have some alien shooting at you. So you have 3 sounds playing, but let's say you only got space for like playing 2 of them. So we need to keep track on and what we call the weight on the sample. It says like if I want to play the background, it has a weight of 2. Me shooting has a weight of 3. And when the alien shooting at me, it has a weight of 1. So I'm looking at these samples like, I shouldn't play this one weighted sample. I just play the 2 others. They're more important. Then I mix those 2 together and write that down into the hardware buffer. And that's mostly for speed, I guess, and for memory bit, because I mean, it doesn't take that much to mix it together. So I need to keep track where in the sample I am, since when I'm at the samples and I should stop playing that, and next time I should play it, I'll play it from the start. And the hardware buffer could be anywhere in between, like the buffer's ends. It could start in the middle playing and play to the end, and then jump and play to the start. So we need to be really careful where we are writing in data into this buffer. And we get how much data we should write in, frames. We getting a bit information of that when this audio callback is called here. So we're going from frame 0 up to frames and filling in the audio buffer. So that's our data, that's our sample data, and we just plus it in whatever already was in the audio buffer. We got the volume, we making sure that it's not too high or too low, and just clamp it, and then write it back into the audio buffer. If you want more in detail, please look at the code. I feel hungry. So yeah, let's go back down to here. So we have loaded the WAV file. You've seen how that is done. I didn't go through how to convert it to something we can load in. Let's do that. That's kind of important. So we got the object dump and type hexadecimal 1 byte each. So there we go. And then we have something called the stream editor. That's called sed. It's a Unix command. It has a command that's called s, which means replace. And we're going to replace 6 digits, I think, because this is just the address into the file. We're going to replace those 1, 2, 3, 4, 5, 6 with absolutely nothing. And we apparently, I didn't type in, was it 7 of them? There we go. But this still doesn't look like any C to me, so I need to modify that. And I'm going to modify the spaces here. Each space here I'm going to modify. And I'm going to say I'm going to put an 0x on that, and before that I'm going to add a comma. And the G in the end means to repeat. Unknown option could be that you can escape this with other characters. Let's try that first. Oh. Well, if you do wrong, you do wrong. There we go. So now we have the file in something. We could dump into a H file or a C file. And then I already done this, of course. And then I just added in this if def include sound 0, so it doesn't compile it twice. Char sound 0, and in the end here added in end if end on it. So that's all. Let's run it. And there we have it. And of course it should be running on the PlayStation Portable also. And since I recorded this before, yeah. Yeah, it's playing. It's a little bit hard to, I need to lean in because it's a bit low. But that I could modify, of course. So that's how you read WAV files in a raw format without any dependencies. And that's how you include them as a C file. And that's how you play things on PlayStation Portable. And the code is in the description if you want it. So be safe out there and code away on the OpenSea.